Right. So my name is Henrik, and this is Patryk, and we're compiler engineers in the Secure Language Extensions group at Apple. We mainly work on fbounds-safety, which is our language extension for bound safety in C. All right, this one. Here's today's agenda. First, I'll give an introduction to fbounds-safety. Then Patryk will do some live adoption, and then I'll show what debugging at runtime errors looks like once fbounds-safety is enabled. So we announced this extension at EuroLLVM 2023, along with an RFC. And last year, we started doing our upstreaming, which is still ongoing. Eventually, we're aiming to fully standardize the syntax and semantics for compatibility across toolchains. But the complete upstreaming is a bit of a long process. So this year, we've completely open sourced our implementation in the Swift fork of Clang as a bit of a staging ground. You can either clone that and build Clang yourself, or you can go to swift.org and download a snapshot development toolchain available for Mac, Windows, and Linux. And while we would eventually like to add support for Objective-C and C++, right now this is only supported for C. So now that you know where you can get your toolchain, let's talk about why you would want to. So memory safety bugs are, across the industry, the leading source of security vulnerabilities, accounting for about 2/3 of all security vulnerabilities. And historically, they've been used in many high-profile attacks to get remote control of victims' devices. And there are many big, established security-critical code bases that we all rely on every day, written in C. Code where security matters greatly, but in a language offering minimal memory safety. And of course, the safest option would be to use a language offering full memory safety. But rewrites of this scale are a massive undertaking, and we need security today, not in a decade. And this is where fbounds-safety comes in. Fbounds-safety detects and prevents out-of-bounds accesses. Unlike other bounds safety mitigations for C, like Fortify Source, fbounds-safety offers a comprehensive model for preventing out-of-bounds access from being exploited by attackers. This improves security by forcing attackers to find other bugs of other types that are harder to exploit. And I want to be clear here, while fbounds-safety can help you find bugs, that's not really its intended purpose. It's meant to be used in production where it can prevent live attacks. Let me show you how this is achieved. fbounds-safety enforces bound safety rules at the language level. And here are the strategies to achieve this. The compiler prevents out-of-bounds memory access at runtime via automatic bounds checking. With fbounds-safety enabled, this is not an opt-in. If the compiler doesn't have enough information to emit a runtime check, or if it has so much information that it knows the access is unsafe, it will tell you this via an error at compile time. If this is the case, the programmer can add the necessary bounds information so that the compiler has enough information to emit a runtime check, and then you can compile your code. The compiler also rejects expressions that don't guarantee the correctness of these bounds annotations, so that the information is reliable once you run into the bounds check. Let me show you what this means in practice. The bound safety extension provides bounds annotations for programmers to apply on function types, struct fields, globals. For example, counted by. Using the bounds information from the counted by annotation, the compiler can insert bounds checks. As you can see, this buggy loop condition will end up going past the end of the buffer, but the inserted bounds check will trap the program instead of accessing the out-of-bounds memory. Programmers must provide this sufficient bounds information. Otherwise, the compiler will reject the code and make the programmer add the bounds annotation. If we use the same example again, without the counted by annotation, the buffer doesn't have the necessary bounds. So when we try to do the array indexing, the compiler reports an error. To make the code work, the programmer needs to add the bounds annotation so that the error can be removed. This way, the extension effectively secures all pointers by default. But it's not enough to add the required bounds information. It must also be accurate. For example, the programmer must also ensure that the count is updated whenever the pointer is, and vice versa. Otherwise, a pointer that started out with correct bounds information may end up with outdated bounds information when one of them is updated, and then you run into a bounds check, and it's not actually the correct bounds. In this example, buff and count are briefly out of sync with each other, since the count is decremented before the pointer is incremented. But fbounds-safety requires that they're in sync at all times. So the compiler reports this as an error. To make the code work, the programmer must move the assignments so that they're next to each other. This way, the extension maintains correctness of the bounds annotations at all times. Luckily, not all pointers need bounds annotations. For local variables, the compiler can track the bounds automatically. And this speeds up adoption since it doesn't require manually adding an annotation, but also because the more flexible semantics doesn't require moving the assignments around, like I just showed you, since there's no external bounds to fall out of sync with. Let's use the same example again. But this time, we'll instead rename the parameters and introduce local variables with the original names of the parameters. Now the type of buff is no longer dependent on count, so they don't have to be kept in sync anymore. And the memory access isn't actually out of bounds, so the code is fine as it is now. There will be still be a bounds check, but the bounds are kept within the buff pointer, so we don't have to move the assignments. This scales a lot better because we only have to make a change at the beginning of the function, regardless of how many reassignments there are throughout the function. And it also reduces the diff with upstream if you're doing downstream adoption of an open source project. So fbounds-safety does impose strict rules on how pointers can be used, but despite that, adoption is still quite easy. Most pointers don't need annotations at all, so the number of places you need to manually edit is pretty small. In our experience, it roughly takes 1 engineer hour per 2,000 lines of code to fully adopt fbounds-safety. For reference, for 1 million lines of code, that's 12.5 engineer weeks. Because it maintains ABI compatibility, you can still use libraries that don't use fbounds-safety. Or if your code base is a library, you can adopt fbounds-safety without breaking the builds of your users. This also enables incremental adoption. So you don't need to open a separate branch where you do the full adoption and then try to merge it back all at once. You can secure your code piece by piece over the course of several releases if you have to. And this is essential for securing large code bases. And this is something we've already done at Apple. Because although the implementation was recently open source, it's been used in production internally at Apple for years at this point. fbounds-safety has been adopted in millions of lines of critical software, running in the hands of consumers on all Apple platforms. And while much of that code is not open source, adoption in the XNU kernel is, in case you would like to take a look at that. Development is ongoing, but the current state of fbounds-safety works and helps keep our devices secure today. All this with an overhead we consider reasonable. I don't want to focus too much on performance, but you can't really mention it without also showing numbers. So let's take a look at a few benchmarks. And before I show these numbers, I just want to mention that these numbers are from 2023, so if you try to repeat them today, they might be slightly different, but they should be in the right ballpark. Anyways, we found an average of 9.1% code size increase and 5.1% runtime overhead. But as you can see from the ranges, overhead varies quite a bit depending on the application. And in general, the impact tends to be smaller in applications that already have manual bounds checks because the optimizer can remove redundant bounds checks. But there's still some work that could be improved in the optimizer to remove more redundant bounds checks. However, in actual adopters, the end-to-end overhead has been less significant than this. For example, we measured the runtime overhead in our audio codecs to be roughly 1%, which we're happy to pay for security. Total binary size overhead is also smaller than these numbers, since this also only measures the text section of the binary. And so we have a handful of bounds annotations with different pros and cons, each suitable for a different scenario that I'm going to show you. Let's start with counted by. Counted by lets you specify an expression representing the number of elements that fit in the buffer. Normally, this is just a parameter or a struct field, but it can also include constants or simple arithmetic expressions. The expression is evaluated in each bounds check, which is why it needs to remain in sync with the pointer. Counted by is great for communicating information between local context because it uses information that's already there and preserves the ABI. So struct fields, function parameters, return values, this is where it shines. It's not just a single annotation though. Counted by is part of a family of 3 other similar annotations, each with slight semantic differences. For example, imagine we want to annotate B0, which takes a void pointer and a size. Void isn't really a type with a size though, so it doesn't make sense to talk about the number of elements in the buffer. Instead, we can use size by. This lets us represent the size of the buffer in the number of bytes rather than the number of elements. Now imagine we want to annotate malloc. Here we pass the size to malloc, but when the allocation fails, malloc can still return null, which isn't really a buffer with a size. So for situations like this, we have counted by or null or size by or null. And for this variance, the bounds check first checks whether the pointer is null, and if it is, it ignores the size parameter. As a rule of thumb, use counted by when you can and the others when you need to. The counted by family of pointers are bounds checked on every memory access, but also for each assignment. In the case of function parameters, that means that the caller will check the bounds before making the call, like in this example where n needs to be checked at runtime. This means that foo can fully trust that the count is correct without knowing where the pointer came from. Next up, we have single. Single represents a pointer to a single element or a null pointer. Because of this, we'll always get a compilation error if we try to perform pointer arithmetic on it. So we can't index into the pointer unless, of course, the index is 0. We could emit a runtime check for dynamic indexing, but we don't allow this because most of the time, if you try to perform dynamic indexing on a single pointer, you're actually just missing bounds information, and we would like to catch that error at compile time rather than at runtime. And if you actually want to index with index 0, just use a constant value rather than a dynamic one. Finally, we have by indexable. Unlike counted by, this lets you index both in the positive and the negative direction, hence the name. This is accomplished by changing the representation of the pointer into a wide pointer, carrying both the upper and lower bound along with the pointer. In this example, the compiler will transform the pointer into a wide pointer and emit a bounds check at runtime when the pointer is dereferenced. It doesn't emit the bounds check during reassignment, however, because if the pointer is out of bounds, that information can still be stored in the pointer, so that if you later access the pointer, the error will be caught at that point. This differs from normal C in that in normal C, it's undefined behavior just to construct a pointer that's out of bounds, but here that's completely fine. So indexable is very flexible. The compiler will allow almost anything because it has so much information to use for runtime checking. However, since it changes the pointer representation, it's not ABI compatible with normal pointers. So the caller must be aware that the function is expecting a wide pointer. This is a problem for backwards compatibility and incremental adoption, because even if the caller and the callee share the same definition in the same header, if the caller is in a translation unit compiled without fbounds-safety enabled, it won't even know what indexable is, leading to an ABI mismatch. So this is a bit of an issue for using indexable in structs and functions, at least in public headers. But the flexibility makes indexable great for local variables where ABI isn't really a factor. Finally, we have an escape hatch we call unsafe indexable. This is just a normal C pointer where you can do anything you normally would with a C pointer, no compile time restrictions, and no bounds checks. This is helpful for interacting with libraries that don't use fbounds-safety, because we can call their functions despite them not having bounds-safety annotations. The library can, of course, do unsafe things with our pointer, but we've done what we can to secure the code that we control. This process is pretty smooth because pointers implicitly convert between different pointer kinds. Let's take a look at how that works and when explicit conversions are required. Here's a model of the core of the fbounds-safety pointer conversions. Byte indexable, being the most flexible kind, acts as a common middle ground between the other kinds. Converting to byte indexable is just a matter of transferring bounds, so no bounds check is needed. On the other hand, converting to counted by style pointer safely requires inserting a bounds check to make sure that the number of elements in the incoming pointer is equal to or greater than the count expression. Safely converting to single similarly requires checking that the pointer actually points to something, since the byte indexable pointer could be out of bounds. Finally, converting to unsafe indexable is just a matter of removing the bounds information. These conversions all happen automatically, so that you don't need to insert any explicit casts because the compiler just knows what to do. But there isn't any implicit conversion from unsafe indexable, however. To forge a safe pointer from unsafe indexable, you need to use an unsafe built-in function. This informs the compiler of the bounds, but it also helps with auditability since you're being explicit about unsafely forging a safe pointer. A large fraction of pointers in function parameters, structs, and local variables don't need any explicit annotations because the default is already correct. These defaults make the adoption process easier because pointers in function signatures, structs, and globals are implicitly single, except for in system headers, then they're unsafe indexable, so that you can still call functions in libraries that you don't control. For this reason, we recommend including all external headers as system headers, unless you manually annotate those headers. Otherwise, the compiler will likely emit a bounds error originating in these headers when you enable fbounds-safety. The defaults for ABI visible pointers can also be changed using pragmas if needed. For local variables, they're all implicitly byte indexable. The compiler is usually able to optimize away the unnecessary bounds if you don't use the full power of byte indexable, so the overhead isn't as big as if it were on the ABI surface. Of course, you can always override these with explicit annotations, but if there's nothing there, these are the defaults. So that was a brief overview of fbounds-safety. There are some additional bounds annotations and semantic edge cases that I didn't cover. So if you're interested in a deeper dive, I suggest watching the initial announcement at EuroLLVM 2023, and of course read the available documentation. The upstream Clang docs reflect the target of our upstreaming work and not the current implementation. With that, I'll hand it over to Patryk.
Hello, I'm Patryk and I work in Secure Language Extension team at Apple together with Henrik. And today I'm going to show you how to adopt fbounds-safety in practice. Oh, sorry. fbounds-safety allows us to do adoption incrementally. Our recommendation is to enable fbounds-safety in a single file. Doing that will likely cause the compiler to emit a bunch of compilation errors and other diagnostics, and those diagnostics will guide you how to annotate the code. And when you fix the compilation errors, you should run the test to check if there are any runtime issues. And here, having a runtime good test coverage is extremely important. And when the tests are successful and the code compiles, you can repeat the step 1 until the fbounds-safety is enabled everywhere. And when you enable fbounds-safety everywhere, you can benchmark the performance such as runtime and code size. And if you are not happy with the performance, you can optimize the code, and we have optimization remarks specifically for fbounds-safety that will guide you how to optimize the code, and they show you where the bounce checks are emitted. So you can also adopt fbounds-safety in libraries, but there is a caveat for public headers. Because system headers, the default attribute in system headers is unsafe indexable. However, for non-system headers, default attribute is single for ABI visible pointers. And this can cause a mismatch if you include your headers in your library that you adopted fbounds-safety as a system headers, because the default attribute will be unsafe indexable. However, if you adopted this already, the attribute should be single. And to solve that, we have a built-in called pointer check ABI assume single, which you can add at the beginning of the file, and this will change the default ABI attribute to single for the whole file. And this will change the attribute regardless whether this file is included as a system header or not. So your public headers in your library should always use this built-in to avoid this mismatch and signal that they have adopted fbounds-safety. And also, libraries have another more lightweight option instead of full adoption, which we call header-only adoption. This is useful for libraries that don't want to pay the cost of full adoption, either in terms of like time investment or runtime overhead. And you can do this by only annotating public headers or public interface, but you don't annotate and don't enable fbounds-safety in your implementation. So the implementation is not secured with fbounds-safety. However, clients that are adopting fbounds-safety will see those annotations and they will get the safe interface. Other clients that are not adopting fbounds-safety won't see those annotations and they won't pay any cost. So one good example is libc. So for example, you can annotate a memcopy with sized by annotation. And this will ensure that on the call side, a bounce check is emitted that you are passing buffers with correct size. But you don't have to annotate, you don't have to enable fbounds-safety in the implementation of memcopy. And this is also useful for safer interop in other languages, because those bounds annotation provide more information to the compiler. But if you want to do header-only adoption, please remember to add a test case where you create a single C file that includes all the headers. This will check that those annotations and in that header at least compile. And with that, this is the incremental adoption, and I will show you a demo live how to do it, but I will show you only the two first steps. So to illustrate the fbounds-safety adoption, we developed a simple program. The program is called B64. It's a simple command line tool that will let you encode and decode base64. And this program is using makefiles to build the project. So maybe I can show you that. So we can build the project. As you can see, this project contains 3 C files, and this builds the B64 utility, and you can use this to encode and decode B64, base64. So we have encoded string, and we can also decode it. And we get the string back. And also this project contains a test script which let us run some tests and check whether everything is fine. So we will do this adoption incrementally. which means we will enable fbound safety in one file, and then we will repeat this process for another file. And so we will enable this, we will get probably some compilation errors, we will address them, and we will run the test every time we enable fbound safety for a single file. And we will repeat this until the whole project is adopted. So let's start the adoption. Maybe let's start this with din-buff-c. This is a simple implementation of dynamic buffer that can grow over time. We have a structure, and we have a couple of functions which let us manipulate the dynamic buffer. So to enable fbound safety, we have to pass fbound safety flag as the compilation flag. So now the Clang will compile this project or this file with fbound safety flag. And we will get a couple of compilation errors, but we can see those errors in Visual Studio Code. So let me show them to you. So here is the first error. And so the problem here is that we cannot index into a single pointer. The compiler says array subscript on a single pointer data must use constant index of 0 to be in bounds. And data here is a function parameter, and which means that function parameters are on ABI layer, and in fbound safety, ABI visible pointers are single by default, what we can see here. So the compiler complains that it cannot prove that this access is safe, and it is correct because we are looping from index 0 to size, and so the pointer must point to at least size element for this access to be in bounds. And we can exactly express this with counted by annotation, and we will annotate this with counted by size. It means now that we inform the compiler that this pointer must point to a size element. And now the compiler will emit a bounce check on the call side to ensure that we are passing correct pointer and size. Moreover, we will emit a bounce check here in the loop to ensure that I is smaller than size. And since here the bounce check condition is going to be the same as the loop condition, the compiler more likely will optimize this check away. So now the function compiles. There is no other problem. So let's see another issue we have here. Oops. And again, compiler says that we cannot index into a single pointer. This time the data pointer is defined in the structure here. And so the structure is used in different headers, and it is on ABI layer, so we don't want to change the ABI. And again, ABI visible pointers are single by default. So we want to annotate this to provide more bounds information, and this structure contains capacity and size, and we will annotate this with counted by capacity because this will allow us to access the whole buffer, and capacity denotes the number of bytes allocated in the data pointer, while the size is the logical size. It says like how many elements are currently used in the buffer. So let's do it. And now, as we can see, the issue is gone. And so let's check other issues. So we have an issue here, and this is actually an issue that is caused by our annotation. And the compiler says that assignment to data requires corresponding assignment to capacity. And from the slides, we remember that counted by has some compiler restrictions. And one of those restrictions is that both counted by pointer and its size or date or its count must be assigned together. And here we have assignment to data, and its count is assigned at the end of the function, and in between we have calls to memset, and this is something that is not allowed by fbounds-safety, so we have to slightly modify the code to make sure that both data and capacity are assigned together. So we can introduce, for example, local variable, and change the assignment to this new local variable. And now at the end, we can assign to the data pointer. And now this new data is a bidirectional indexable pointer because this is local variable, and by default, local pointers are bidirectional indexable. And we don't get those compilation errors because bidirectional indexable are flexible. However, the compiler will emit a bounce check before assignment to data and capacity to ensure that the new data contains at least new capacity elements. And if this is not true, then we will trap at runtime. So now this problem is fixed. We can see whether we have another issue. And yes, we do. There is another issue like that. Again, we cannot index into a single pointer. And here, again, buff is a function parameter, which means it has like single attribute by default. However, this function is a static void, static function, which means it's not on ABI layer, and we can actually change this pointer representation to a white pointer. So we can annotate this with bidirectional indexable, and the problem is fixed. The compiler will emit a bounce check here before we are accessing the buffer at index I. We could also use counted by annotation. So we can, for example, annotate this with counted by. And yeah, this issue is also solved. And the question is whether we should use bidirectional indexable or counted by. And our recommendation is if you can use counted by because there is a size available, you should use counted by instead of bidirectional indexable. One reason behind this is that bidirectional indexable is the size of 3 pointers, and counted by is ABI compatible with raw C pointer. And other reason is that usually counted by could be better optimized by the optimizer. So now we don't have any other issues here in this file. So remember, from the incremental adoption process, we can test the file whether it works. So we run the test, there is no issues, so we can incrementally adopt fbounds-safety and in another file. So let's do it. Let's adopt this in base 64, and base 64 is basically the implementation of base 64, and we have encode function and decode. So the first step is to add fbounds-safety flag. We will do it. And now the compiler will compile this file with fbounds-safety. And we don't have any issues in this file because we don't do any pointer arithmetic in this file except for data at I, and this doesn't cause any compilation diagnostic because we already adopted fbounds-safety in this file, and we have already the counted by annotation, so no issues, no new issues here. But however, the compiler will emit a new bounce check to ensure that I is smaller than capacity here. So it's a good idea to run the tests to ensure that we still don't have any runtime issues. And yeah, we adopted successfully fbounds-safety in 2 files. So let's continue this process and let's adopt fbounds-safety in the last file, main.c. And now we have a couple of issues in this file. So let's see what the compiler says. And now we have a similar issue to the previous issues, that we cannot index into a single pointer, and argv must use a constant index of 0 to be in bounds. So we have to annotate this, and we know the annotation we should use. It's counted by. And now the issue is gone. Here we have another issue. The compiler says that we are trying to initialize a bidirectional indexable pointer with incompatible type unsafe indexable, and local pointers are bidirectional indexable by default. However, we initialize this from std_in, and std_in is defined in std_io, which is a system headers, and by default system headers are unsafe indexable. So if std_io adopted fbounds-safety, this won't be an issue, because std_in and std_out would have, and here fopen would have the bounds information, but std_io doesn't adopt fbounds-safety in this example, so we have to provide additional bounds information to the compiler. And since unsafe indexable can point to arbitrary many elements, so we don't have bounds information, we have to inform the compiler that std_in and std_out points to exactly one file pointer, and we can use unsafe forge single. Oops. To say, please use this pointer and assume bounds of a single pointer. And we can use this to fix other problems as well. So we will use this here. And here. So now the problems are fixed. This build-in is necessary to inform the compilers about the bounds of the pointer, but it is also useful if you want to do code auditing, because you can just grab the source code for unsafe, and it will show you the places where you are converting from unsafe to safe pointers. And now we can compile this project and run the tests, and all the tests are successful. So we achieved our goal, and the program is bound safe. And with that, I will hand it over to Henrik to show you some debugging.
Right, so now the compiler is happy, but that doesn't mean, and the tests pass, but there's actually still a bug in this program, because we only had 6 test cases. It's not very good test coverage. So we're gonna debug a runtime trap in this code, and you can either imagine this happened in a better test suite with more extensive coverage, or if this was a replay of some attack that was prevented. So we have this, we'll create a file. And create some carefully crafted input from our attacker here. Oops. There we go. And then we should be able to, are we missing the, whoops. That's a shame. Let's see if we can fix this live. And the executable is called B64, right? And I'm not used to this keyboard layout. How do I? There we go. We'll fix it like this. That's fine. And then let's give it some output as well. All right, let's see if that works. There we go. All right, so we see that we've encountered a trap here. We get this nice error message saying bounds check failed, dereferencing above bounds. And this is using the new, as of last year, verbose trap functionality in Clang. So this is exists in upstream Clang and LLVM, and it works by encoding the message in a fake inline stack frame. So you can see here we've got this inline stack frame with the message, and in normal LLVM, it would know to skip this stack frame and go directly to the real stack frame, but the VS Code extension isn't aware of this, so let's go there manually. And then we can see here's where the trap actually occurred. We're indexing into B64 table. That one is actually in bounds, but this is the out of bounds access. And then we can see for this dist pointer, we have here it says right with the downstream version of LDB, it would show the bounds here. So this will be part of our upstreaming process. It would tell us this is counted by capacity for data here, and we see that capacity is 8. We can see that J is 9, so we're out of bounds, and that's why it trapped. And the problem here is we have this dynamic buffer, right, that grows when we add things to it, but this function is actually just directly accessing the internal data pointer instead of using the public API. But before I show you the fix, I want to show you the disassembly of this function. So we can see here we stopped at this breaking instruction with the immediate operand OX5519, and this is a value that's reserved for fbounds-safety. So if you see this in a stack trace or something, or core dump, then you immediately know that this is an fbounds-safety trap. And in this function, let me give you some more space here. We can see there's a bunch of different break instructions with their own separate messages. But if this was in an optimized build, this is just a completely unoptimized debug build. If this was in an optimized build, they would all be merged into one break instruction with branches going to the same instruction. So we would lose source information. And if you want to see where the trap actually occurred and why, you either need to do an unoptimized build, or if that's not an option, you can use f-unique traps as a compiler flag, and then it will prevent the merging of these traps. So let's see if we can let's see here, what's the where do we toggle the terminal? Oh, is it there? Oh, there we go. Perfect. go. Let's go back to the, where was, all right, we need to make, and we can run this again. And now we should have some output here. There we go. And here's our encoded value. Let me just quickly show you what the fix was. So instead of just accessing the values directly, we now use the official DynBuff push API. And so when we add new elements, it will actually grow the buffer. So this was a quick demo to show you how fbounds-safety prevented the out-of-bounds access, and how to identify fbounds-safety traps, and how LLDB can help you find these issues. Let's go back to the presentation. Right, let's see here. Right, so this was just a small demo project that we created to fit within the time frame of this presentation. But if you want a bit of a bigger project, we have adopted fbounds-safety in the open source project GIFlib, which is an established C code base for processing GIF images. And that's available at our GitHub here if you want to take a look. And then, as I mentioned before, we also have adoption in XNU. So in conclusion, fbounds-safety enables incremental adoption for large code bases as well as small, and helps you catch bound safety issues in production before the attacker is enabled to exploit them. If you found this interesting, there will be some more similar content in our colleague Devin's keynote tomorrow, and a recipe for eliminating entire classes of memory safety vulnerabilities in C and C++. So definitely check that out. And yeah, go ahead and try it out. Give us feedback. You can talk to us here at the conference or whenever at the fbounds-safety channel on Discord. And thank you for all your attention. We'll now take questions.
Hi, question. So what is the limitation of this expressive language for counted by? Like, can I do counted by this variable designates, you know, the power of 2 of the array length? Because a lot of legacy code does like wacky encodings of,
right.
Or like also things like, you know, I don't use a local to store the, you know, the array size. Like, oh, I use a global because a lot of old C programs like to do that. And then like, what is the idea to expand it with like, I don't know, more features? Or is it the idea that everyone writes like, you know, clean C code where you have pointer length?
We do have some limitations that we don't want to give up. Like, for example, you can't just call arbitrary functions. The only time you can call a function as part of the expression is if it's annotated as pure, and I think there's some other restriction on that. But basically, like, it has to be able to be evaluated at compile time. So no runtime function calls. You can do some arithmetic, you know, plus minus multiplication. Maybe bit shift is, yeah, I think bit shift is probably fine. So like power of 2 could potentially be done. With global variables, there are some restrictions where the pointer variable and the count variable have to be in the same scope, because otherwise it's really hard to track that they're updated at the same time. If the global variable is a compile time constant, like if it's a const variable that's, you know, in the constant section and everything, you can use it. But if it's a mutable variable, then it's really hard to check that they're updated together.
Well, unless someone else asks something.
Hi, yes, great, good talk, thank you. So how well are variable length arrays supported in flexible array members? Can you comment on that?
Yeah, so counted by supports flexible array members. So you can refer to other struct fields in the flexible array members. Yeah. Is there anything specific that restricting those?
No, I don't think so.
Yeah, no, it's like they work as long as you have the some kind of information in the struct about the length of it. You can annotate that with counted by.
All right, great, thank you.
Hey, I was wondering if you have to modify your original design based on a text that you saw in the real world, or did you come up with a spec and after shipping that you never saw any exploitation of memory in production?
So you're saying, did we do an implementation and then realize, oh, we don't actually cover?
Yes.
Not that I'm aware of. We have found cases where it's like, oh yeah, we didn't actually have bounds check in some cases, but we haven't found any cases where that was also simultaneously used in attacks. Yeah, we both haven't been part of the entire project since the beginning, so we haven't seen the really early stages. So yeah, we could talk to some other colleagues that have been part of it a longer time later, see if there's some information there, but I don't know of any.
I see. And another question, why does unsafe forged single require specifying the type explicitly? Can't it infer it from the point on type?
Depends. Unsafe forge could be used also when you can forge a pointer from an integer. So you don't necessarily have to use the same type. So for example, you can have void star as the pointer value, and you can forge file pointer.
I see. Okay, thank you.
I just want to ask, so you've completed this exercise. The next step would be that you benchmark. And suppose that you notice there is some performance overhead that you don't like. You mentioned you could get some insight in where the runtime checks are and something about optimization remarks to help avoid them. Could you say a little more about that? I would be interested.
Yeah. So we have optimization remarks that will tell you where the bounds checks are emitted. And so you can look into it and maybe rework the code and so on to or refactor the code slightly to be able to optimize it better.
Suppose that you have a bounds check in a tight loop where you really want the bounds check to be outside of the loop, before the loop or something. How can you accomplish that?
So maybe you can change the, so if you have counted by and you see there is a bounds check, so you can, for example, change the loop condition, maybe, or change the count used in counted by, and it will maybe optimize this bounds check. Or also sometimes you can reorder the loop, and in that case, if you iterate from size to 0, then the bounds check is usually hoisted outside of the loop.
Okay, thank you.
Or you could, if it doesn't do that for you, you could manually do a bounds check before the loop, and then the ones inside the loop become redundant. There are also cases where if you have really complex count expressions, like if you do division inside your count expression, that's going to be really expensive. So maybe you could figure out a way to work around that. But yeah.
Hi, sorry, just to keep on top of time, we might just have time for one more question. If any other questions, you might just take it outside.
Cool.
Thanks for the presentation. And my question is about C++. Do you know, are you aware of any obvious challenges in making this work with C++? Or have you just not looked at it yet?
The biggest challenge is just there are so many more constructs in C++. So we recently added support for just syntactically using the expressions in C++ templated functions and parsing them properly. That wasn't supported before, but even then, it's not really supported for runtime in C++. Covering the entire language is going to take a while.
But could you just do it for the C-ish subset of C++?
Probably, like if there's a need for that, that could absolutely be done. But then you'd have to figure out, like, okay, do we just error if you're using templates or whatever?
Thank you.